are there. These are the existing data. Okay. So this is your existing data. Now what has happened? This data is stored in the system. The system will not execute anything. It will store the data as it is. Okay. Now if any new data is given to the system and it has to be classified, then what it will do? It will find, it will compare with the existing data. So what it will do? It will take the nearest data. So here, if you see in this particular data, the nearest data to this particular new instance is, it will be comparing with this. Okay. Again, it will be comparing with this. Again, it will be comparing with this. So now these are the nearest neighbors to the new instance. Okay, so now what it will do, the nearest neighbor's output is classified to the new instance. So which particular the new instance belongs to? Star class. Why? Because if you see these nearest neighbors, one is circle and the other are star. Okay, so the new instance is belongs to star class. So in this way, the new instance is compared with the nearest neighbors. Okay, if it is comparing with the nearest neighbors, then it is called as locally weighted regression. Okay, if it so if it is comparing with the local variables, then it is called as locally weighted. Okay, if it is comparing with all the attributes, the new instance is compared with all the attributes. Okay, so then it is called as global. Okay, so the phrase locally weighted regression is called local because the function is approximated based on only the data near the query point. So this is your query point and this is compared with your nearest neighbors which are local to that. Okay, so then that is called as locally weighted regression. Okay, so now let us consider the case of locally weighted regression in which let us consider the case of locally weighted regression in which the target function f is approximated near x cube using a linear function of the form f cap x is equal to, this is your formula. So now let us consider the case of locally weighted regression in which the target function f is approximated which is nearer to x cube by using linear function. So what is linear function? Linear function will be in the form of, you can see ax plus bx plus c or ax plus b or ax plus bx plus cx plus d. So likewise, so these are all called as linear functions. Okay, so these are all linear equations. Okay, so it is linear equation without any polynomial terms. What are the polynomial terms will be having? Like x square, x cube, x to power of 4. So likewise. So we in linear function, these polynomial terms will not be there. Okay. So the linear equation without any polynomial term The equation which is not having any polynomial term, then it is called as linear equation. Okay, so it is linear equation. The training, whatever the target function which is there, that will be always linear equation in case of linear regression. So here what we are doing, we are using linear regression. So when we are using linear regression, we will be using different types of linear equations only. Okay, so this is one of the linear equation where we are considering here. So this is linear equation. Okay, so here if you see f cap of x, what is this f cap of x? That is estimated value of x. Okay, and w naught plus w1 a1 x plus so on w1 a and x. So what is this? This is nothing but linear combination. Linear combination of weights and different attributes to that particular instance. W is nothing but your weights, A is nothing but your attributes, X is your instance. Instance lo any attributes, any attributes we will be assigning the weights here. Okay. So here, if all the other attributes does not play any role, in extreme case, then only W naught is used. W naught is a constant value. W naught అనేది ఎప్పుడు work అవ్వదు. When we are using the function, W naught will not work in all the cases. When the other weights and attributes are not working, then only W naught constant value will be working extremely based upon different terms which are there in the data. Okay. Now we derive methods to choose weights that minimize the squared error summed over the set D of training examples such as gradient descent to minimize the error. So in the starting class, in previous classes I have told you, we will be using gradient descent to minimize the error. Okay. So here what is error? We are giving some data to the model and we are executing with some method and we are getting some output. Okay, and that is our predicted output. The predicted output is not accurate to the target output. Whatever the output which existing output is there, that is not uh, accurate with the existing one. Okay, so then there will be some error. So what we have to do, we have to minimize that error, then only we can get the accurate result. So for that purpose, we will be using gradient descent technique. Okay. So when we use a regression, here we use least square method. Regression use చేసినప్పుడు least square method ని ఖచ్చితంగా use చేస్తాం. Okay. So when we use regression, we use least square method in which we try to minimize the sum of squares. Sum of squares of that particular error. Okay, so ఒకసారి ఎగ్జిక్యూషన్ ఆఫ్ ఎర్రర్ వచ్చింది, ఇంకోసారి ఎగ్జిక్యూషన్ ఆఫ్ ఎర్రర్ వచ్చింది. సో మనం ఏం చేసినట్టుగా ఇవన్నిటిని మినిమైజ్ చేస్తాం, ఇవన్నిటిని సమ్ చేసి దీన్ని మనం మినిమైజ్ చేయాలి ఈ ఎర్రర్ ని. ఓకే, సో నౌ వాట్ we are doing, once executed we will get some error. Okay, and the difference between the original value and the predicted value, now sum them. That will give you the sum square error for the particular model. For this, So this is my data. A is student, okay, and some value is there. So some not student, some data is there. B 2, and for first instance the value is 20. For second instance the value is 40. C 3, then 30. D 4, 50. So likewise we are having some data. Now this data is given to the model, okay, and we are implementing locally weighted linear regression on this particular data, okay. So now what has happened? We have executed this and we have got some output, okay. So first instance is given and I have got some output as 15, okay. So this is the predicted one, but the actual one is 20. Now what we have to do? We have to find the difference between this and this. The difference is 5. Now what you have to do? We have to decrease this 5 value. Okay. If we decrease this 5 value, then what will happen? It will again come to some 18 or 19. So what will happen here? The error is decreased and we have got somewhat similar to the existing one. Okay, so that we have to do here. So we have to decrease the error here. For that purpose, we are using f cap of this, and we are adjusting different weights to different attributes. ఒక్కొక్క attribute కి కొంచెం కొంచెం weights మనం adjust చేస్తున్నాం. Okay, and the to find the error, the formula is half of sigma x belongs to d f of x minus f cap of x whole square. So what it is? A is error, that is similar to half. X belongs to sigma of x belongs to d is nothing but for every instance belongs to d. For every instance belongs to d. Except instances that belongs to d. F of x is nothing but your existing value until 20. F cap x is nothing but your estimated value, that is 15. Okay. Now what you have to do? You have to find all the values for different instances that errors should be summed here. Then you will get the exact error for all this data. If you reduce, again you have to reduce that particular error, then you will get the accurate result. Okay. So for that we are using gradient descent training rule. So this is the formula which we will be using. Whenever there is any prediction error, so to reduce that, we adjust the weights. Okay, so there we will be using gradient descent training rule. So this is the new which we will be using, that is learning rate. The learning rate should be adjusted according to the weights. Okay. How shall we modify this procedure to derive a local approximation rather than a global one? The simple way is to redefine the error criteria E to emphasize fitting the local training examples. 3 possible criteria are given in next slide. Note we write the error E of x2 to emphasize the fact that now the error is being defined as a function of the new query x2 power of q. So now if you see, there are 3 points when we are using locally weighted linear regression method. So what is the first point? Minimize the squared error over just the k nearest neighbors. So what we have to do? Don't try to minimize the predicted error over all the training examples. What you have to do here, just try to minimize the squared error only for the k nearest neighbors. Japan. So this is a new one. Okay. If you want to which particular this new instance it belongs to. So what we are doing here, we are finding the nearest ones. So this is one nearest one. So this is one nearest one we are having. This is one more nearest one. This is one more nearest one. Okay. And this is one more data which we are having. So likewise, we are having different type of data. Okay. So what we are doing here, we are finding this new instance with the nearest ones. This is called as locally weighted linear regression. ఏవైతే న్యూ ఇన్స్టాన్స్ ని లోకల్ గా ఉన్న వాటిని కంపేర్ చేస్తామో దాన్ని మనం లోకల్లీ వెయిటెడ్ లీనియర్ రిగ్రెషన్ అంటున్నాం. Okay, so now here minimize a squared error over just the k nearest neighbors. So you minimize these k nearest neighbors with the new instance. For that we will be using this formula. So what is that? Even of xq. Even of xq and the estimated value for new instance. Okay, that is equal to half of sigma x belongs to k nearest neighbors of xq. And the x and the set of training examples. You are not considering all the data. You are just considering the set of training examples, not taking entire set of training examples. You are considering only k nearest values. Okay, so that is x belongs to k nearest neighbors. So these are the k nearest neighbors of xq. This is xq. xq and a new instance. Sigma of f of x minus f cap of x square. So what you are doing, you are trying to calculate the error in prediction. So this is used to find the error in prediction. Okay, so for this what you are doing, you are considering only k nearest neighbors. K nearest neighbors is only error to find out. Yes. Okay, now if you consider another one, minimize the squared error over the entire set D of training examples while weighting the error of each training example by some decreasing function k of its distance from xq. So now what you are doing, considering all training examples. So in the first case, what you have did, only you have considered the local one. Now what you are doing, you are considering all the training examples, but adding the distance. Measure. If the distance measure is far, if the distance of new instance with the existing one, so this is the new instance. So this is your new and this is your existing one. So if the distance of new instance with the existing instance is far, add less weight to that. If it is nearer, what you have to do, you have to add more weight. Okay, then you will get the error. Error when you are using all the training examples. So then this is the formula which you will be using. Okay. Now what you have to do, combine one and two, combine these two. So initially what we did, initially in this case, we calculated the prediction error only for k nearest neighbors. And then we have calculated the prediction error here. Okay. Next what we did, we have calculated the prediction error for all the training examples by associating some weights to each instance based on the distance from new instance. Now what we are doing, we are combining this and this. Both we are combining here and we are trying to give some weight to the k nearest neighbors. Okay, so listen carefully. So in the first case, we are taking only the nearest ones, combining with the new instance, and we are getting some error. In the second case, what we are doing, we are taking all the training examples. Here only few examples are taken which are nearer one to the new instance. But here we are taking all the training examples and we are comparing with the new instance. All are compared with the new instance and you are assigning some weights to this. దగ్గరగా ఉన్న వాటికి less weight ఇస్తున్నారు, దూరంగా ఉన్న వాటికి ఎక్కువ weights ఇస్తున్నారు. Okay, and you are finding the error. Now what you are doing, you are combining this and this. Again you are assigning the weights to that which are nearer to this particular new instance. ఇట్లా కంపేర్ చేసినాక మనకి ఏ ఇన్స్టెన్సెస్ అయితే దగ్గర ఉన్నాయో మనకి తెలిసిపోతుంది. ఆ ఇన్స్టెన్సెస్ కి మనం ఏం చేయాలి, వెయిట్స్ యాడ్ చేస్తే మనకి రిజల్ట్ అనేది accurate గా వస్తుంది. సో దిస్ ఇస్ ద ఫార్ములా విచ్ యూ విల్ బి యూజింగ్ ఫర్ యాడింగ్ ద వెయిట్స్. సో దిస్ ఇస్ ద weight value we will be assigning. So this is the weight value which we will be assigning to the nearest ones. Okay, to be compared with the new instance. So this is your new error which you will get. If that is less, then your result is accurate. So this is locally weighted linear regression. So this approach requires computation that grows linearly with the number of training examples. K nearest neighbors also increase lots of computation. So lots of computation have to be nearest neighbor are. So criteria 3 is a good approximation to criteria 2 and has the advantage that computational cost is dependent on the total number of training examples. Its cost depends on the second one. Why? Because here we have considered all the training examples, but in case of first, we are considering only few. Then computational cost will be less. Okay, so that is nothing but criteria 3 is a good approximation to criteria 2 and has the advantage that computational cost is independent. Okay, so its cost depends on only on the number k of neighbors considered. K అంటే ఏంటి, ఎన్ని నియరెస్ట్ నైబర్స్ మనం కన్సిడర్ చేసినాము న్యూ ఇన్స్టాన్స్ తోటి కంపేర్ చేయడానికి. సో అది ఇంపార్టెంట్ ఇక్కడ. Okay, so K is very important here. So if we choose criteria 3 and rewrite the gradient descent rule, we obtain the following training rule. So this is the final formula which we will be using to find the error with adjusting the weights, with which we can find which are the nearest neighbors to the new instance. Okay, so this is the formula which we will be using here. Data WG and data and gradient descent rule. This is nothing but your learning rate. These are the different weights which you are assigning to the nearest neighbors. Okay, and this is the formula. This is the distance between the existing one and the new one. Okay, so this is about locally weighted linear regression method. Next is this is a small topic. Next is radial basis functions. So one approach to function approximation that is locally related to distance weighted regression and also to artificial neural networks is learning with radial basis functions. So it is same as linear functions or multi-layer, that is neural networks, which we have seen in the previous class. So those methods also will be using distance weighted regression technique. So here also, while using gradient basis function, we will be using distance weighted regression method only. So it is using distance based metric. ఇంతకుముందు KNN లో కూడా మనం డిస్టెన్స్ ఫైండ్ అవుట్ చేస్తాం ప్రీవియస్ ఎగ్జిస్టింగ్ వన్ తోటి కొత్త దాంతో. ఓకే, సో it is using distance based metric as we are using in KNN, like Euclidean distance. It will be using kernel function between new instance and the existing one. So KU is nothing but your kernel function. Is the distance between the new instance and the old instance. And W naught is a constant value. Okay, W is the different weights which we will be assigning to different instances, different attributes. Okay, so this is a formula which we will be using for radial basis function. So next one is case based reasoning. So instance based methods such as k-nearest neighbors and locally weighted regressions share three key properties. So before going to that, just I'll give you one example why we will be using case-based reasoning method here. So if you take your friend, okay, your friend has a problem. So he or she asks you some suggestion. Okay. So what you will do? He or she will ask you some suggestion how to come out that particular problem. Okay. So what you will do? You will memorize. You will recall. So anywhere such type of problem is solved by taking any particular solution, any particular specific solution. ఓకే. సో మీరేం చేస్తారు? రీకాల్ మీ ఫ్రెండ్ వచ్చి మీ దగ్గరికి వచ్చే ప్రాబ్లమ్ ఉంది అని అడిగినాక మీరు ఏం చేస్తారు? యూ విల్ థింక్ ప్రీవియస్‌గా అట్లాంటి ప్రాబ్లమ్ ఎక్కడైనా అరైజ్ అయిందా? దానికి ఏమైనా సొల్యూషన్ వచ్చిందా? ఓకే. సొల్యూషన్ వస్తే ఆ సొల్యూషన్‌ని మీ ఫ్రెండ్‌కి చెప్తారు. ఓకే. So likewise, if you take if somebody or if your friend is asking to you which university is best, okay. So now, uh, what they will do, they will ask some suggestion to you. So now you will find out where what you will do. Now you will find out where your previous friends or relatives joined in different universities. That you will think how they filtered and how they have selected the best universities. That you will think, that you will recall, that you memorize it. Okay, those cases you think what are the approaches they have used to solve the problem, for finding your solution to how to join in. So what they will do, they will recall all these things. You will recall all these things and you will tell this is the particular approach, how they have used, what are those approaches they have gone through some portals, they have gone through some brochures, they have gone through some references of your friends, they have seen different types of websites. So all these things. So these are the different approaches they have gone through with your previous friends or your relatives have gone through. Okay, and this approach you will tell to your friend to select the university. Okay, so this is the particular application you follow and you try to memorize it. And in the same way, you suggest your friend. Okay. So what is having in this case? You are you are trying to match the present problem with the problem or which has been followed for that particular problem. So if it is feasible, you try to apply that particular that particular solution same to your current problem. That knowledge we are applying here. That is why it is also called as. So in order to perform some reasoning task, in order to find out some solution to your current problem. So this is all called as case-based reasoning technique. Okay. So here in instance-based methods. So till now we have seen the previous techniques, k-nearest neighbor spanning, locally weighted regression planning. So these are all instance-based methods. Instance-based methods such as k-nearest neighbors and locally weighted regression share three key properties. They are sharing three key properties. What are they? First, they are lazy learning methods in that they defer the decision of how to generalize beyond the training data until a new query instance is observed. So what all these are all nothing but lazy learning methods. That means only what they will do, only the training until new instance is given. Processing does not start. They will just store the data and when new instance is given, then only it will compare the old data with the new data. They will observe the existing one with the new one. That's why they are called as lazy learning methods. This is the one thing. What is the second one? Second, they classify new query instances by analyzing similar instances while ignoring instances that are very different from the query. So second, what it will do, it will analyze the existing one. Any particular instance is similar with the existing one, those will be retrieved, and the instances which are not similar to the present one, that will be ignored. Okay. Third, they represent instances as real world valued points in an n-dimensional space, Euclidean space. So here they represent instances as real valued points. It's A2 attribute only, A3 attribute only. So it's attributes only. Okay. Then data itself is going to be 1, 2, 10, 4, 10, 15. So it's a data is going to be. So these are all real value data. Okay. So if you take one more example, Sunny. Sunny ఒక attribute. Okay. Next, Yes, can you hear me? Hello. Hello. Can you hear me? Yeah, okay. So next to us is also mine. I'll take class at 12:15 or 12:20. All of you join by 12:15 or 2:15 or 2:20. Okay.